Okay, so welcome everyone to our first lecture in Math 2421, Differential and Integral Calculus. So today we're going to be considering the subject of limits, finding limits, both graphically and numerically. And to do so, and because we're all like related to data science one way or another, we're going to use a programming language. We're going to use Julia. So after downloading Julia at julialang.org, let me go ahead and share my screen now. You should see a little Julia emblem, either in your applications folder, or you'll be able to find it on Windows pretty quickly if you just search Julia. And you'll see these little three dots here. Go ahead and click on that, and it will open up your terminal, which will be, which is the Julia REPL. Okay, so the Julia REPL is the most simple way to interact with Julia, but it's a very powerful way to interact with Julia. So yes, there are what are called IDEs that we can interact with Julia, but I think the REPL will be fine for us in this course, because I'm not assuming that any of you have any programming background. We're just going to more or less use it as a calculator. So before we get started, I think that we should just look at like the basics of using the REPL. So we can do like arithmetic, like 1 + 1. We can multiply numbers by just 3 times 4. We can divide numbers. We can even look at a rational expression. So if you do double backslash, you'll have a rational. So if you want to add fractions in the REPL, it's pretty easy. So if we wanted to add 1/2 plus 3/4, it'd be 5/4. And that's pretty cool, especially for those of you that might not be fans of rational expressions. Now, if you would like to clear out the screen that you have, just press Control L and it'll clear out the screen. So the mode, the Julia REPL has several modes. Right now we're in the Julian mode, I'm sorry. And this is the calculator that we'll be using. But there are several other modes that we should be aware of. Most importantly, well, not most importantly, but the first one I'll mention is the package mode. So I'm going to put it in quotes here. That symbol, the right square bracket, if you type the right square bracket in the Julia REPL, you'll go into what's called the package mode. So the package mode is where you will add packages to your Julia environment that will be useful for us. So there are 2 packages that I think that we need to use. The first one will be plots. So we're going to go into the package mode by hitting the right square bracket. And to get out of it, you press delete, by the way. So hit the right square bracket, go into the package mode, and then type add PLOTS plots. So this is adding the Julia plots package, the plots.jl package to our Julia environment. Now, the next package I'm going to suggest that you add, you don't have to, but I think it's a great package, is called REPL. So if I go back to the Julian mode and I type something like print line to print ln string hello world in quotes like that, goes off the parentheses. Notice that this print line is a function that's built into Julia, but it didn't highlight. So I like to know what the functions are when I'm using the REPL. And one way to do that is to go into the package mode and add something called capital O, H, capital M, Y, and then capital REPL. So, oh my REPL. And by the way, mute your mics if you're not speaking. So this package, oh my REPL, gives syntax highlighting to your functions and your.
I'm sorry, I have a question.
Yes.
Can I share my screen real quick?
Yeah.
Okay, hold on. So whenever I do it, this keeps happening. I don't know what's
Oh,
going on.
it's loading right now.
Oh,
So
so just wait.
yeah, I already had plots installed, so it was really quick for me to install it. But you're installing it for the first
Oh,
time, so it's downloading all of the dependencies.
oh, okay. Thank you.
It shouldn't take too much longer. It should take like another minute or so.
Oh,
Okay. So back to REPL. So to use this package inside the Julian mode, type using REPL. So capital OH, capital NY, capital REPL. So now when I call my functions, so print ln, notice that the syntax now highlighted. So REPL is just a package I like to use to see syntax highlighting inside of the Julia REPL. Just makes life a little bit easier. Okay, so if you now when I type using, see that it highlights, whereas before it didn't, and that's because I'm now using this package. And since we're going to be looking at graphs later in lecture, you can go ahead and also type using plots after you've added it to your Julian environment. Okay, so now I'm using plots, using on my REPL. So those are really the only two packages that we'll ever really use in this course. So that's the package mode. Those are the two packages that we'll need. The next mode is the help mode, which will be really useful for those of you that are new to Julia and new to programming. And the way to enter the help mode is to just hit the question mark key. So if I hit the question mark, so shift backslash, which is the question mark on my keyboard, I'm in the help mode. Press delete to get out of it, question mark to go back into it. So suppose like I didn't know what the print line function was, or the print ln function was, I could go into the help mode and then type print ln like that, and then press enter or return. And the help mode tells me what's going on. So it searched for these things. It found something. So what does it do? Print, using print, followed by a new line, okay? And then it gives examples. Print hello world, print other stuff. And the help mode is really useful when you don't know what the functions do, like you might see me use in lecture. So for example, later on in lecture, I'm going to use the plot function from the plots package. So if I type question mark and then plot, I get a description of what the plot function does. So the help mode is really useful. And again, to clear out your window, when it gets filled up, just type Control L and it will all clear away. So far we're using REPL and we're using plots. And those are the only two packages that we'll need for today's lecture and for the rest of the semester, really.
How did you say we get out of package mode?
Press delete.
Thank you.
What was the key for package? You said something with brackets and then
The right square bracket on your keyboard. So if you just hit that key, the right square bracket, you'll go into package mode, and you can press delete to get out of it. So once you go ahead.
To add the REPL, we just do package add REPL.
Right, so go into the package mode and do add capital OH, ONY, and then capital REPL. Add REPL. Since I already have it installed, it takes like a second for it to install. And then to use REPL, you go back into Julian mode and then type using REPL, and you'll get the nice syntax highlighting after you press enter or return.
Okay.
If you're curious about what I just did, I press backslash PI and then I press tab and it makes a nice little pie. It's a cute little feature of Julia. Backslash PI and then press tab. Okay, any more questions about the Julia REPL? Okay. Well, unless there's any more questions, I think that we should start talking about limits.
I couldn't get that pie to work. I must be doing something wrong.
Oh, I'll do it one more time. So, and it's not very important, but you just, so backslash
Okay,
PI
PI,
and then press tab.
tab, nothing.
Well, we'll talk about it maybe after we finish lecture because it's not too important for today, for now.
Okay,
Okay. All right, so now let's talk about limits. Okay, so if at any point during lecture, if the screen becomes blurry, go ahead and speak up and I'll stop and I'll make sure that it focuses. All right, so this is lecture 1. We're talking in this lecture, we're going to study or begin our study of limits. So before we can actually get to the core of calculus, which are derivatives and integrals, before we can get there, we have to have a solid foundation in limits. Limits are kind of like the bridging topic between pre-cal and calculus. Between those two things, we have limits. So in order to understand limits, we should probably start with an example. So consider the function f of x equals to x cubed minus 1 all over x minus 1. Okay, so this is just some rational function, x cubed minus 1 over x minus 1. Can you tell me what the domain of this function is? Any guesses? The domain is basically, if you recall from pre-calculus, it's the set of all x values that you can plug in there and everything's fine. What's an x value that we cannot plug into that function?
0.
Well, we could plug in 0, right? Because then we'd have 0 minus 1 over 0 minus 1.
1.
X equals to 1, we cannot plug in, right? So f of x here is defined.
It's blurry.
It's blurry.
Here, f of x is defined as all x not equal to 1. Right? Because if we plug in x equals 1, we get what? 0 over 0. Right? And we all know that we can never divide by 0, right? So in pre-calculus or algebra, we would just say, okay, just forget that value to put into that function. In calculus, we can think about it, or we're encouraged to think about it. So the question at hand right now is, okay, so maybe maybe I should word it like maybe can we consider f of x at x equals 1? So if so, how? Okay. Well, the way that we're going to do this is we're going to look at the behavior of f as x approaches 1, right? Because this function is defined everywhere outside of 1. So why not look at x's like at, I don't know, 0, at x equals to 0.5, at x equals to 0.75, at x equals to 0.9. That function is defined at all of those. So maybe we can say, like, where is that function going as x approaches 1? So the answer yes, we can consider this function at x equals 1 in a particular way. So we do so by answering the following question. Well, maybe not answering, by considering the behavior of f of x as x approaches 1. Okay. Okay, so and there's two ways to do this. So we can do this in two ways. Graphically and numerically. Okay, so in the graphical approach, we plot this function at every value except for x equals to 1, and we just kind of look at the curve of that function as x approaches 1. In a numerical way, we build a table of values as x approaches 1 and f of x evaluated those values, and we see like where the logical value is. Now, again, because this is a course that's kind of targeted at data scientists, let's use a programming language to kind of explore this problem. So I'm going to share my screen. Okay. Now, the function that we were considering was x cubed minus 1 divided by x minus 1. So in Julia, we can define functions very easily. For example, this function, we could do f parentheses x equals 2 parentheses x to the power 3 minus 1 divided by parentheses x minus 1. And then press return or enter. So we have now defined our function f. And we can evaluate it as you would expect. So like, what's f of 0? It's 1, right? So it'd be 0 cubed minus 1 divided by 0 minus 1, which is minus 1 over minus 1, which is just 1. What about f of 3? It's 13. What about f at 1? That's the bad one, right? Nan. So this is like basically, it's a non-numeric value because we, again, as we were just speaking about, f is not defined at x equals to 1. Okay, so I've defined my function, f. So maybe we can plot it. Now, f is not defined at 1, but the plots.jl package that we added, so using plots, we'll still try to plot this function. So if we type plot, which is a function that's imported from this package. So if we do plot f,
How did you do the x squared? How did you get that to?
it's the caret. So on my keyboard, it's Shift 6, and it makes a little caret.
Okay, thanks.
Just be sure to put it, the numerator in parentheses and the denominator in parentheses after you get that caret there. And make sure that you have the plots package added so we can use the plot function, which is imported from this package. And then we can just pass in f. All right, so plot f. And the first time that you call a function from a package, where'd it go? It takes a second for it to load. So here is my plot. Let's see if I can squeeze this in over here. All right, so there's my function. Now we know that f evaluated at 1 doesn't exist, right? So this plot is kind of fake, not fake. It's not the appropriate plot. We know that we're missing a value here. Right? We know that we can't define this function at x equals to 1. So this is just an approximate plot to this function. Okay. Now, just to speak a little bit about the plot function from plots.jl, we can make our plot nicer. For example, we can plot f, and then we can do something like label. And this is a keyword argument. Label equals to f of x equals to x cubed minus 1, close parentheses, backslash x minus 1, all in string, so all in quotes. So now we see that we have a nice little legend here depicting what we're plotting. So in general, like, not for this class, but I'm going to try to emphasize it a little bit, but in your future classes that are anything related to data science, you want your legends, you want your plots to be descriptive. So if you can include a descriptive legend detailing what you're plotting. Okay. Also, if you want to like change the x limit, so like what like the smallest x is and what the biggest x is, we can plot f and then give the x limbs keyword argument. And maybe I just want to look at x from, I don't know, -6 to 6. And maybe I'll put my label there again. So now you see that my plot changed. My x limits are now -6 to 6. Make my plot a little bit bigger. And then you can do the same thing for like the y limits. You can like specify what the y limits should be. So for example, if I want to add y limits, I just use this call here so I can see how my cursor is blinking and I have like an empty cell in a sense here. If I, on my keyboard, press up, it goes to the last thing that I ran. If I press up again, the one before that, up again. So that's like a quick way of doing it. So I press up, I get that. And now I can come over here and add y limbs. So maybe I want to say y limbs equals to, open parentheses, maybe like -5 to 50, close parentheses, comma, and then press return. And now we can see that the y limbs changed.
So my F3 is coming up as 4.7. So that's, I'm not able to go any farther. I'm not sure why that's happening.
Be very careful that your function is defined just like this.
Okay.
So
Yeah, see, I did my function when I did like the caret to do x squared. It's
X-
not.
x
It's not.
cubed.
Oh, it's a 3. Oh, okay. I can't see. Sorry.
Here, I'll make it bigger actually. So
I have my glasses on and I'm still blind.
is this better? I made it a little bit bigger.
Yes, yes, thank you.
You're welcome. Okay, so there's my resulting plot, and this is me adding y limbs. But just for now though, we can just plot and look at the thing, because what's the question at hand, right? Like, yes, I had to kind of have a little bit of a tangent on using this function, but the question we're trying to answer is considering this function f at x equals to 1. So like, where is this function going as we approach 1? So maybe maybe we should like zoom in on this little region here, right? Let's zoom in here. So that's between 0 and 1. So I can just do like plot f x limbs equals parentheses 0 to 2, I mean. So this is now zoomed in. So this is the function f. I hate this legend. Actually, I don't want to type this over and over again. It's kind of a pain to type. So I'm going to do something like name equals to parentheses f of x equals to open parentheses x cubed minus 1 divided by x minus 1 close parentheses. So now I have a variable that's been assigned to the string. So now I can go to plot, and then I can do label equals that variable, which I called name. That way I don't have to type this over and over again. Okay, so here is the plot generated by this function. We know that there's something weird going on here because this function is not you can't evaluate it right there at x equals to 1. But the question that I had earlier was that, okay, where is this function going as x approaches 1? So at 0, what's the function's value? It's 1, right? At 0.5, the function's value is like, I can just evaluate it real fast. F at 0.5, 1.75. So this is like 1.75 right there. And then 0.75 or so, what's the value of the function? 2.31. 2.31. Okay, so we're going this way. Where do you think this function is going as x approaches 1 as we go this way? Just by looking at the graph. Like,
Positive,
say that again?
positive infinity.
Well, so like if like f at 0.5 is 1.75, f at 0.75 is 2.312. What about f at 0.85? 2.57.
Going to 3.
Yes, it looks like from the graph that we're going to 3. And also, if we look going this way towards 1, right? Like if we take x to be bigger than 1 and we start decreasing it. So like, what's f at 1.5? So it's 4.75. What's f at like 1.25? So like right here. F at 1.25, 3.8. So it's like 3.8. So as we're getting closer to 1 from the right-hand side, let's do f at 1.01. So that's like right up next to it. See how it's like close to 3? So as our x are going closer to 1 from this way, our y's are going towards 3. And as we're increasing x going towards 1, our y's are also going towards 3. So the graph is telling us that, oh, we're heading towards 3. Even though, as we just saw, f at 1 is not defined, from the graph of it, we can get like a sense of where the function is going. And in fact, we can do this now numerically, which was the second way of looking at this problem. So let's say, let's make some x's going towards 1 from the left-hand side. So I'm going to make a variable called x underscore left. And I'm going to say, okay, we just got to pick some x's getting closer to 1 from the left-hand side. So like maybe like 0, 0.0, 0.5, and there's commas in between these, 0.75, comma, 0.85, comma, 0.95, comma, 0.99. Okay. Close that bracket out. So I just made a variable called x left, which is a array of numbers that are getting closer and closer to 1. So I'm going to press return. So we have a vector. That's what these things are called. 0, 0.5, 0.75, 0.85, 0.95, 0.99. So, okay, let's now loop through each of these values and see where the function is going. Now, I know some of you have no programming background, but just bear with me here. We're going to do what's called a for loop. So for, I don't know, whatever variable name you want to give for like maybe, I don't know, for x in x underscore left, press return. And now we're inside the for loop. And now I'm going to tab over, just press tab to give yourself some white space so you can see how those cursors there now. Just press tab and you can press delete to go back, but we want to be over here. For x in x left, we're going to do print ln f of x. So x is a variable coming from this thing, and we're just going to print line the function at each of these. So x that, x that, x that, x that, x that, x that. So now we're not done with our for loop. Now we have to close it out by hitting return or enter. Press delete to go back a space. Notice my cursor's there. And then I'm going to end my for loop. So for loops, looping in Julia requires ending out your statement. So this is called a code block, and we have to end out that code block. So let's see what happens when I press return. So when x is equal to 0, f is 1. When x is equal to 0.5, f is 1.75. When x is equal to 0.75, f is 2.31. When f is equal to 0.85, when x is equal to 0.85, f is 2.57. X is equal to 0.95, f is 2.85. And then finally, when x is 0.99, f of x is equal to 0.97. So we can see that we're getting jumbled up, right? Like 1 to 1.75 to 2, and then like we're not jumping anymore. You see that, right? We're getting squeezed up against a value. So we can do a similar.
Sorry, I have a question. So
Yes.
whenever you did the x left and then you put the numbers, you don't ever have to call the function that you're putting the x in, or it remembers the function?
So the function is here. So
Okay.
yeah, so like this, so the for loop is just scrolling through each of these. So for example,
Okay.
like you can give whatever name you want to it. So like for, I don't know, variable in x underscore left, print line variable. And then in that for loop, and you see these are the variables in there, 0, 0.5, 0.75, 0.85, 0.95, 0.99.
Well, I guess I'm saying it knows to use the equation. Like, how does it know to use the equation that way?
So we've defined f above, right?
Oh, okay. That's what F is. Okay,
Yeah,
never mind.
so F is good, right? So now, if
Okay.
we're going to evaluate F, all of these variables inside there, we just do for, I'll just change the name to variable in X underscore left, print line F at that variable, and then end out my for loop, and then we have this.
Oh, okay. Thank you.
You're welcome. So let's do a similar task now from the right. So like from the left-hand side, we see that we're getting closer to 3. Let's do from the right-hand side. So let's make another vector of values called maybe X right. And let's say like 1.5. And we want to get smaller. We want to head towards 1 from the right. So 1.5, maybe 1.25, maybe 1.10, 1.05, 1.01, 1.001 maybe. So we just made a bunch of values that we're going to check and see where our function is going as we head towards 1, right? These are all getting closer to 1, and now we're going to look at the function at each of those. So let's do another for loop. So for variable in X underscore right, print line F at that variable, and then end out the for loop. Okay, so now we can see like it's 4.75, 3.8125, 3.31, 3.15, 3.03. It's going towards 3. So in both cases, we see that the function that we've defined f is heading towards 3 from the left and from the right, which kind of, we see that it's heading towards 3 from the left and it's heading towards 3 from the right. So this is evidence to us to say the following. So what this is telling us, so we've observed f of x is going towards 3 as x goes to 1. That's what we've observed. Okay. Now, this is the central idea behind what are called limits. So informally, we've shown limits as x approaches 1 of this function this is just as it reads, the limit as x approaches 1 of x cubed minus 1 divided by x minus 1, it's 3. That's where the function is going. Now, this kind of answers our question, like considering this function at x equals to 1, we can't just plug it in because we have an undefined function when x is equal to 1. But we can still consider the behavior of the function as x approaches 1. And that's what this is saying. Now, it's important to like make this distinction that the limit is not the same as evaluating the function at that point, right? Sometimes the limit will actually equal the function at a given point, but it's not the case in general that you should really make the distinction. The limit is different than evaluation. The limit is a process. Evaluation is plugging in. Process, plugging in. Two completely separate things. Okay, and I can't emphasize that enough. So let's look at another one. Maybe let's look at this. Limit as x approaches 0 of x over the square root of x plus 1 minus 1. The square root is only here. Okay. So we can try to, so again, this, maybe I should say a little bit more about this. What we just did was considering the behavior of a function as x approaches 1, this other function, right? At the very end, that's what I told you is what's called the limit. So here, this thing is some function, right? There is some function. I don't know, call it like h or something, right? And this function's domain, well, we cannot plug in a 0, right? If we plug in a 0, we have root 1 minus 1. Oh, that's going to be division by 0. So we can't just plug in a 0 here. So what we want to look at is the behavior of this function as x approaches 0. That's what this notation is asking us to evaluate. So then whenever you see the limit, it's asking us to evaluate a process. The process of looking at this function as x approaches a certain value. Okay. So let's go ahead and use Julia to do this. Okay, so here we are. I'm going to press Control L to clear out my screen. And now I'm going to define a new function. I'll call it h. H of x equals to x divided by, open parentheses. Actually, let me try something real fast. Okay, so this is the square root function, sqrt. I forgot the syntax for it, so I wanted to make sure that that was built in Julia. All right, so I'm going to define my function h of x now equals to x divided by, open parentheses, sqrt, so that's the square root, open parentheses, of x plus 1, and then all minus 1 inside of those parentheses. So square root, parentheses, x plus 1, minus 1, close out parentheses for the division. So there's my h. And as before, we can just evaluate h at given values, like h of 1 is that. But if we look at h of 0, we should have a problem, which we do. All right, so let's go ahead and plot h now. There's a quick plot of h. Now, just looking at the picture here, what do you think the limit as x approaches 0 is for this function? Just take a guess. As x approaches 0 from the left and the right, where are we going?
2.
2, right? Like immediately we can see that the function is heading that way, right? So now we can kind of play the same game we were doing before, and let's just like take x getting closer and closer to 0 from the left and then from the right and see where this function is going. So x underscore left, we want to go towards 0 from the left. So maybe like negative 1.0, negative 0.5, negative 0.25, negative 0.10, comma, negative 0.05, negative 0.01, I don't know, negative 0.001. Maybe I'll go even further, negative 0.0001. Okay. So we're approaching 0 from the left. So now we can do that same for loop that we did last time. So for variable in x underscore left, press return to enter into the code block, tab over. We're going to print line h evaluated at that variable. And then backspace to end out the for loop. So let's see where we're going. 1, 1.7, 1.8. We're getting squished up against 2. Y'all see that? Squished up against 2. As x is approaching 0, the values for the function are getting squished against 2. On the left, we have to look at the right now. So let's do from the right. So x underscore right. Maybe we'll do like 1.0, 0.5, 0.25, 0.10, 0.05, 0.01, 0.001, and then finally 0.0001. The vector of values getting closer to 0 from the right. And then we can just do our for loop again. So for variable in x underscore left, press return to go into the code block, print line h evaluated at x underscore, oh, sorry, not left. I have to backspace to delete that, x underscore right, because we're going from the right, this guy. All right, so let me tab over, print line, h evaluated at the variable. Backspace in the for loop, and let's see where we're going. Obviously, we're also getting scrunched up against 2, right? So from the left and the right, we're both approaching 2. You see that? It's consistent, consistently getting closer to 2 from the left-hand side and consistently getting closer to 2 from the right-hand side, which agrees with the graphical image that we have here. Okay. And again, I'm recording this lecture, so this will be on my YouTube channel, and all of you can go and view that and do these same things that I'm doing here, because I know that I'm typing faster than you guys. You're not used to programming yet, so this video will be available for you guys. So just based off of our graphical and numerical interpretations or calculations, we can say that that's equal to 2. That's like an informal way of evaluating the limit. There is a formal way, but that's an informal way.
So are we going to be having access to Julia on the test?
Oh, yeah,
Or no?
of course.
Oh,
Of course.
okay.
So let's look at another example. Now let's look at maybe like a piecewise function. So maybe say let f of x equal to the piecewise function. Say,
Well, that's what I need. That's what I need to hear. Oh, about that.
so let's say f of x is equal to 1 if x is not equal to 2, and 0 if x is equal to 2. Now this is a really easy function to plot. So I don't even need Julia to do this. So So here's x equals to 1, 2, 3, 4, -1, -2, -3, 1, 2, -1, -2. So this function for all x that are not 2 will be mapped to 1. So what does that look like here? At -3, the function value is 1. At -2, 1. At every value except there, it's going to be 1. And then at x equals to 2, the value is here. So now we can actually evaluate this function everywhere. This function is defined on all real numbers, right? Defined everywhere. So what's the, so what about this now? What about the limit as x approaches 2 of this function? What is that limit going to be for this function? Just by looking at it.
0.
So if we evaluate the function at 2, it is indeed 0, right? However, remember earlier I said that this is a process which is different than evaluation. I remember I kind of emphasized that a few minutes ago. So, okay, let's just play the same game, right? Imagine okay, this is our function and we're heading this way, right? So actually we can use Julia. Let's use Julia to study this limit. Okay. So let me press Control L to clear out my REPL. And then now let's define our function. Now, this function is a piecewise function and it requires more syntax to define it. So I've already shown you how to define quick functions like this, right? Whatever, you can do this. That's a quick way to define a function, but sometimes you want to define more complex functions. To do that, you need to type the keyword function and then give it its name. I'm going to call it f in this case. It takes in a variable x. Now I'm going to press return and then tab over. So I'm inside a code block now. So I press return and tab over. So now I'm going to give the definition of this function. And I'm going to do this with an if-else statement, which all of you will learn about whenever you take a programming course. But I'll give you the quick rundown of it here. If x exclamation point equals, that's not equal to 2.0. So this is the if statement. So if x is not equal to 2, so exclamation mark equals right next to each other, that means not equal. So if x is not equal to 2, press return and tab. So now I'm inside this code block for the if statement. So if x is not equal to 2, return 1.0. Press the return key, backslash. So now see how I'm lined up with the if? So now I'm going to do the else. Else, so if it is equal to 2, return 0.0. Okay. Now this is considered a code block here. So in Julia, we have to end out code blocks. So if x is not equal to 2, return 1, else return 0. So if it does equal to 2, return 0. Then end out that code block, and then press return, backspace, and now end out your function definition. So again, the function is a code block which needs an end statement. The if else is also a code block, which needs an end statement. So each code block needs an end statement. And you can tell when I'm in a code block because I tab over. So I tabbed over to get inside of this function code block here as well. But then here you see I tabbed over because now I'm inside this code block. So, all right, that's my function. So maybe we can plot f, maybe it'll plot it. That's not a nice plot, right? So we should probably change our y limits and our x limits. So plot f x limbs equal to the tuple. We're only concerned around 2, so maybe I can do like 0 to 3, maybe. And then y limbs equal to -1 to 2, maybe. I'm plotting f and I'm specifying my x limits now. X limbs, it's like it puts the bounds on your x and the bounds on your y. Smallest x, largest x, smallest y, largest y. Press return. So again, this function, this graph here is not great because we know that if f is equal to 2.0, I mean, if x is equal to 2.0, the value is 0.0. So here, the value really should be right here. But this is the plot generated. So the plot's not going to really, like, it does help us in a sense, but it's not what I wanted to emphasize. I wanted to emphasize that the limit as x approaches 2 is a process and not just something that you evaluate and plug in. So let's do the same game. Let's approach 2 from the left and the right. So x underscore left. Let's say 1.0, 1.5, 1.75, 1.88, 1.99, 1.999. That's x left. And then we can say for variable in x underscore left, tab over, print line, our function that we defined, f of that variable. And then end out our code block. So, okay, let's do it from the right now. X underscore right. So we're approaching 2 from the right, so maybe 3.0, 2.5, 2.25, 2.10, 2.01, 2.001, maybe one more, 2.0001. Okay, so for variable in x underscore right, print line f at that variable. Okay, so based off of this information here, right? Here's x approaching 2 from the left. Where does it look like the function is going?
1.
Right. And then as we go to 2 from the right-hand side, where does it look like the function is going?
1 also.
Also, so when they match up, when the left and right-hand sides approach the same number, they're both approaching, the function is approaching 1. As we go to x equals to 2 from the left and the right, that's going to be the limit. So here, the limit is in fact 1. Even though f of 2 is equal to 0. It's a really important point to make here. Okay. All right, so let's go ahead. I'm going to pause the recording. Okay, welcome back. So during our break, I was curious if there was a package, a Julia package that could help us with limits and like verify our intuition. And like, as we're learning these things, if there was any way that a package could help us. And what I came across was something called SymPy. So SymPy.jl is a package that can help us solve limits, among other things. What you're viewing right now is the documentation on GitHub. So GitHub is something that all of you will become very familiar with if you're a data science major. It's basically a way of collaborating on programming projects and storing open source packages. And Julia is an open source language, so all of the packages that are written in Julia, you can install and you don't need to pay for anything, and it's really nice. But this package called SymPy, I went to my REPL and I added SymPy. So I went into my package mode. I added SymPy, capital S-Y-M, capital P-Y. It took a second for it to install. And then I typed using SymPy in the Julian mode. Took a second to install a few things. But then after, so again, package mode, add capital S and P, and S-Y-M, capital P-Y, just like that. I already have it installed, so it took a while for it to install. And then I just typed using SymPy. And then now that I've imported this into my current namespace, I suppose, there is this limit function that this package imported. Okay, SymPy.limit, so it's a function. So the way that this works is that let's just go and define our original function that we started with, f of x equals to x cubed minus 1 divided by x minus 1. And again, this function is not defined at 1. But now, because we have imported the SymPy package, we can do limit of f as x approaches 1. So the first argument is your function, and then the second argument is the limit. Limit is 3. And that's what we observed earlier, right? So we can verify our limits using this nice Julia package called SymPy. And again, this function limit comes from importing the SymPy package into our current namespace. Okay. So I think that's kind of cool. And it's a way of like verifying the intuitions behind the graphical and numerical explorations that we've been doing. So it's a nice little tool to have, right? And again, you can use this package whenever you want to. This is a part of being a data scientist, looking up packages that can help you with the tasks at hand. So I don't have any problem with you using this package on like an exam or homeworks or anything like that. It's here, it's been written already, and it's there to help you verify the intuition that I hope that you start with, which is graphical and numerical, and then you can verify your answers using this package. Okay, so that's kind of cool. All right, let's continue our discussion of limits. Or looking at more examples and what can happen. So the next example, let's consider f of x equal to the absolute value of x over x. All of you know what the absolute value is, by the way, right? If not, speak up and I'll redefine it for you. Absolute value, yes, no.
Yes.
Means no negatives, right?
Sort of. And I think that maybe I should redefine it, even if you have an intuition behind what that is. So, recall the formal definition of the absolute value. It's equal to x if x is greater than or equal to 0, and negative x if x is less than 0. That's the formal definition of the absolute value. So how does this work, right? So let's just consider an example. Absolute value of like 1.5 is equal to, so this is a piecewise expression here, function. So is 1.5, the point that's on the inside, is that greater than or equal to 0 or less than 0? It's greater than or equal to 0, so we return whatever's inside. What about absolute value of -2? Well, in this case, the x is a -2, right? So -2 belongs here. It's less than 0, right? So we're going to return negative of x. Negative of whatever's on the inside. See that? So what's negative times -2? Positive 2. So that's the formal definition, but in simple terms, it just equates to, it is the positive value. It's always the positive. So if it's negative, it becomes positive. But the more important way of thinking about the absolute value is the distance from 0. Okay, it's this here. It's so important. I'm going to write it again. Like, this is a way of measuring distance. Super, super, super important, and will come up a lot throughout the semester. The absolute value is distance. So, like, what do I mean by that? So here's 0, right? 1, 2, -1, -2. Real number line. So, okay, let's look at 1.5 right here. How far away is 1.5 from 0? 1 plus 0.5. So that distance from there to there is 1.5. Okay? What about now -2? What is the distance from -2 to 0? Distance is always what? It's always a positive number. You can't have negative distance. Okay? So what's the distance? 1, 2. So the absolute value is the distance from 0. Have any of y'all ever thought about what the absolute value is, the distance?
No.
Okay, well, I'm glad that I told you that, because that's how you should think about it. Absolute value is a measure. It's what's called a measure. It's a distance, okay? And it is precisely the distance from 0 when you're just taking the absolute value of a single number. Okay? So a little refresher on the absolute value. Now back to our function. Okay, so the problem at hand is to determine maybe the limit as x approaches 0 of this function. So without drawing a graph, without calculating anything, just take a guess at what do you think that's going to be. Like, can we plug in 0? No, because then we have division by 0. But like, what do you think this limit is? Just take a guess. Maybe I shouldn't ask that question yet because this is different than the ones that we've looked at prior.
Can I
What was that?
infinity?
Does not exist.
It doesn't exist, actually. And let's look at why. Let's look at the graph. Okay, so when x is positive, right? So when x is positive, the absolute value is just the same as what we put into it, right? Whenever x is like 1, this is just going to be a 1, right? In the numerator. When x is 2, it's just going to be a 2, right? And in the denominator, it's going to be the same value, right? When x is positive, that is the same as that, correct? So when x is positive, what's the value of this function?
One.
1, right? Like it's just number divided by itself is just 1. So it's just going to be like, we don't know what it is at 0, but we know that everything this way is just always going to be 1. Okay, what about when x is negative? So when x is negative, the numerator is going to be positive and the denominator is going to be negative, right? So what's the value of this function when x is negative?
-1.
What?
-1.
Exactly, it's going to be -1. So for example, if like x is equal to -2, we'd have 2 over -2, which is -1. So that's the graph of the function right there. So again, this here is asking if it's a process, right? It's like where the function is going as x approaches 0. So, okay, let's look at the left-hand side. As x is approaching 0 from the left, where is the function heading toward? What's the value of the function heading towards?
-1.
Exactly, -1. And x approaching 0 from the right-hand side, where's the value of the function going?
1.
1. So from the left-hand side, it's going to -1. From the right-hand side, it's going to 1. Those are not the same numbers. In the previous examples, they were the same number. Now they're going to different numbers. So there's no single number that these two sides converge to. So what we say is that this doesn't equal anything. This does not exist. There's no single number that this function approaches as x approaches 0 from the left and the right. Okay. In fact, I'm curious as to that senpai.jl package. I wonder what it's going to say. So let me share my screen. Okay. So Control L to clear everything out. And let's say f of x is equal to absolute value of x. So ABS is the absolute value function divided by x. I wonder what happens if I try to plot this. Where is my plot hiding? Oh, there it is. Oh, it did the best it could. There's a vertical line there. So, okay, because I'm using this SymPy package, it has a limit function. Let's pass in f and then pass in the limit of 0. Ah, that's not correct. So this is very important. This is actually a very important thing to notice. Just because you have access to something that can calculate limits, if the limit doesn't exist, then it's not going to work. So this is not usable when the limit doesn't exist. So you still have to be able to verify like graphically and numerically what these things are. You can't just like defer to this limit function from SymPy. So maybe we should just numerically verify things. So like x left, I don't know, negative 1.0, negative 0.5, negative 0.25, negative 0.05, negative 0.01, negative 0.001, negative 0.0001, or variable in x underscore left, print line f of variable. That's definitely going towards -1, right? I wonder what happens if I do. Because like I'm about to do x right, and it's basically the same thing, right? I'm gonna go from the right. So what if happens if I do x right equals to -1 times x left? Oh, that works. It's the positives now. So now I just multiplied everything in here by -1. So now I can do for variable in x underscore right, print line f of the variable. Where is it going? 1. So now we've like verified numerically that the limit does not exist. This is going towards -1, and these are going towards 1. You have to read it down to up. Because, oh no, we're still good. Okay. So this is an example of a limit that does not exist. Let's look at another case. Let's look at f of x equal to 1 over x squared. So here, let's look at the limit as x approaches 0 of this function. Okay. So I know what this graph looks like immediately, but I'm not sure if all of you do. I wonder if Julia can help us. I actually have no idea what's going to happen when I try to plot that. So let's see. Okay, so f of x equals to 1 divided by x squared. Plot f. Let's change our x limits to get a better view of it. Plot f x limbs, let's say -1 to 1. Still not great. Say x limbs, this is probably not going to help at all. -0.5 to 0.5. Same thing. So our plot really isn't helping us at all. So, okay, graphically isn't helping us. Does anyone know what this graph looks like?
Yes.
It's like, well, actually we can and we can plot this. We can be a little bit creative about this. Let's plot the function from 1 to like 0.1. So +1 to 0.1. So okay. What I can do is I can say maybe like, what do I want to call it? Maybe domain. Now I'm going to use a built-in function from Julia called linRange. Lin, capital L-I-N, capital R-A-N-G, linRange. So the way this function works is you provide the first value on the x-axis that you want to start with, say what did I say, 0.10. And I want to go to 1.0. And then, so this is the first value. This is the second value. And then in between these, I want a bunch of points, maybe like 100. And I'll call this like domain underscore right is equal to linRange, like that. So notice it starts at 0.1 and it goes all the way to 1.0, and there's 100 points in there. So now what I can do is I can plot domain underscore right, and then I can take my function, here it is, f, and do f dot, this is called broadcasting. So I'm taking the function and I'm applying it to each of these. In fact, I should probably show you that first. So there's the domain right. And if I want to apply f to each of the entries in there, I do f dot open parentheses domain underscore right. And it applies f to each of those values. So f at 0.1 is there, f at 0.109 is there. So we can plot a vector of x values together with a vector of y values instead of just plotting the function. So plot domain underscore right. So those are my x values, and then f applied to domain underscore right. So now it just links up all of those. So we have x values and y values, and it just connects them in the plotting fashion there. Okay. Okay. And then I can do the same thing for the left domain. I can just multiply this by -1 and get a left domain. So domain underscore left is equal to -1 times domain underscore right. And what I can do is I can modify this plot by plotting over it. So the way to do that is with the exclamation mark. So plot exclamation mark takes your most recent plot and then it plots whatever else you want to do on top of it. So I'm going to do domain underscore left and then f applied to domain underscore left. So it modified the original plot, and now we can see this is our second plot shown in right. So this is more or less the function. We applied f to this right-hand side and applied f to the left-hand side, and we get a better looking view. So we can see that as x approaches 0 from the right-hand side, where does the function look like? Where does it look like it's going? As we head from the right to 0.
But it never touches 0, right?
Yeah, x never equals 0, but as we get closer and closer to 0, where does the function look like it's going?
It looks like it's approaching 0.
Well, as x is getting closer to 0, where are the y values on the blue side? Like, where are the y values going?
Oh, I think to infinity, right? They're
They
going
are.
straight.
They are definitely getting larger and larger and larger and larger. And if we look at the right-hand side, as x is getting closer to 0, where are the red y values going?
Going up as well.
Also going to infinity. So what's happening here,
Boundary of infinity.
yeah, they're both sides are going to infinity. This is not a number. So this means that they're both going to infinity. This is not a number, so the limit does not exist in this case. And if you wanted to, like, you could just like see that. So for value in domain left, print line f applied to value. You see that as the smaller and smaller we go, the bigger and bigger we're getting. We're just getting larger. It's not getting jumbled up anywhere, right? As we're getting closer to 0, it's not stopping. It's just growing and growing and growing. And this is indicative of a function that's just arbitrarily getting larger. Okay, so this is another example where this limit simply just does not exist. Okay. All right. And then one more example. So f of x is not equal to sine of 1 over x. And we're curious about the limit as x approaches 0 of this function. Okay, so as before, we have technology, we might as well use it. Let's see if Julia can plot this thing at all, because I'm assuming that most of you would have no idea what the graph of that looks like. Okay, so Control L. All right, so now let's define our new function, f of x. So luckily in Julia, all the trig functions are already built in. So I can just do sine of 1 over x like that. And then I can just evaluate it. Sine's built in. Nice. All right, so let's see if we can plot it. I doubt this is going to work at all. Oh, it actually did something useful. It worked. I did not expect that. Let me specify my y limbs a little bit differently. Plot f y limbs equal to say negative 1.25 to 1.25. And I'll give it a label this time too. Like that. All right, there's our function. So, okay. As x is approaching 0 from the right-hand side, where does this function look like it's doing? Like, where is it going? This is the full graph of it, by the way. Well, if we can't see it graphically, we can also look at it numerically. So x right equals, I don't know, 1.0, 0.5, 0.25, 0.10, 0.01, 0.001, 0.0001. Okay, so for value in x right, let's print line f at that value.
So this one would be oscillating, right?
It's oscillating, exactly. In fact, maybe we can specify our x limits to be a little bit closer around 0 to help us see that. Our numerical exploration here shows that it's positive, negative, positive again. It doesn't look like it's being jumbled up anywhere. If we go back to our plot, I don't know, maybe x lim is equal to points, like negative 0.5 to 0.5, that. We can kind of see it a little bit better, right? It's just oscillating between negative and 1 forever. So what that means is that there's no number that this is jumbling up on from the right-hand side and from the left-hand side. This limit does not exist as well. So this is another example where you have oscillations which tell us that this does not exist. So we've seen 3 different ways for which limits do not exist. The left and right-hand sides go to different numbers. That was the first way that we saw. The second way was that the function blows up, it goes to infinity. And then this is the final way where we have oscillation. So these are the different ways for which a limit won't exist. The best way to determine if a limit exists really is just, as we were showing earlier, looking at from the left and the right-hand sides as they go, as you approach the x value, the function, if they're heading to, the function values are heading towards the same value, that's indicative that the limit does exist and it's equal to that value that it's approaching. Okay, so I think that'll be it for today's lecture. In tomorrow's lecture, I will give you the formal definition of what it means for the limit to exist, as well as also start with limit rules, where we can just like calculate the limit quickly without having to do these numerical experiments. So that'll be for next time. And I'll go ahead and stop the recording here.